On this slide, I'm explaining the header file, gpio-daemon.h. This file defines the interface for my own low-level GPIO class. First, I include Arduino.h because the Arduino SAMD core provides the SAMD21 register type definitions that I need, such as port group. It also provides constants, such as high and low. Next, I defined an enum called GPIO mode. GPIO input mode is 0, and GPIO output mode is 1. I use an enum so the function calls are clearer and I do not need to pass unclear magic numbers into the code. The GPIO-daemon class has 3 public methods. Config GPIO configures a selected MCU pin as either an input or an output. White GPIO drives the selected pin high or low. Read GPIO reads the current logic level from the selected pin. There are also 2 private helper methods. Get port group converts a port letter, such as A or B, into the correct SAMD21 port group address. Its valid pin checks that the pin number is in the valid range from 0 to 31. This helper methods lets the class validate the requested port and pin before writing to hardware registers. On this slide, I will explain gpio-daemon.cpp, which contains the actual implementation of the class. The key point is that I'm not using Arduino pin mode, digital write or digital read. Instead, I am directly accessing the SAMD21 GPIO registers through the CMSIS style registers definitions. Get port group returns port to group 0 for port A and port to group 1 for port B. If the input is not A or B, the function returns null pointer so the program does not accidentally write to an invalid memory address. In config GPIO, I first create a pin mask by shifting 1 left by the pin number. For example, PA17 becomes bit 17 in the register. I then clear pin configuration and pin number, which disables peripheral multiplexing and allows the pin to operate as a normal GPIO pin. If the selected mode is output, the function writes to direction set. On the SAMD21, direction set configures the pin direction as output. If the selected mode is input, the function writes to direction clear and enables the input buffer by setting input enable. White GPIO use outset to drive the pin high and out clear to drive the pin low. Read GPIO reads the in register and checks the selected bit using the pin mask. This is the part that demonstrates direct register level GPIO control. On this slide, I will explain the main Arduino sketch. I still use the normal Arduino setup and loop structure, but the actual GPIO control is done through my own GPIO-daemon methods. First, I create a GPIO-daemon object called GPIO. Then I define LED port as A and LED pin as 17. This is because the built-in LED on the Arduino Nano 33 IoT, also known as D13 or LED built-in, maps to PA17 on the SAMD microcontroller. In setup, I call GPIO config GPIO with port A, pin 17, and GPIO output row. This configures PA17 as an output. It is similar in purpose to Arduino pin mode, but internally my function writes to the SIT329 direction set register instead. In loop, I call GPIO white GPIO to set PA17 high, then delay for 1000 milliseconds, so the LED stays on for 1 second. After that, I call GPIO white GPIO again to set PA17 low, then delay for another 1000 milliseconds, so the LED stays off for 1 second. This creates a repeating 1 second on and 1 second off blink pattern. The important point is that the blink program does not use pin mode, digital write or digital read for LED control. It used the GPIO Dagon class that I implemented. On the final slide, I will show the compile and hardware demonstration. First, I will click Upload to show that the code compiles successfully. After the upload finishes, the built-in LED should repeatedly blink with 1 second on time and 1 second off time. Thank you.